So we're going to look at, I don't know how many there are, probably about eight rules here that are going to help us find some integrals. The first one is kind of a simple idea, I think. We have this function f of x, and we want to integrate f of x from a to a. What is the area of the region from a to a going to be here? What we're looking at here is just going to be a straight line, and a line doesn't have any area, right? So I like your idea, Cole, but it's wrong. It is just going to be 0. So the integral from a to a of any function, doesn't matter what the function is 0. It seems kind of arbitrary to say this, or kind of useless to say this, but that is going to be useful to us. The integral from b to a. Now, when we're using a and b for these rules, typically we think of a as a being smaller than b. So we'll say here that a is smaller than b, and it really doesn't matter if a is smaller than b here. But if we go from b to a instead of a to b on f of x, so we want to integrate from b to a, what's going to happen to our area? It's going to be negative, or at least it's going to be negative if the function is above the x-axis. But instead of saying it's negative, how could we relate it to this integral here? The integral from a to b of f of x with respect to x.
It's the opposite.
It's the opposite, exactly. So whatever this integral is, if we flip the limits of integration, it's just going to be the opposite. That's going to be useful later on when we get to the fundamental rule of calculus, or the fundamental theorem of calculus. It's also going to be useful if we end up with an integral where we have a smaller number on top. We can just flip it and put the smaller number on the bottom and take the opposite of that. Okay. This one here, we have a sum of integrals. And so we're going to integrate the function f of x. And we're going to do it twice. We're going to integrate from, oops, probably shouldn't put it there. We're going to integrate from a to c, and then we're going to integrate from c to b, and those two added together is going to equal what? The integral from a to b of f of x. This is an important rule because if we do have a function that's not that is continuous but it's not differentiable, and we have a corner somewhere, or we have a piecewise defined function, we can split it up where the functions are split up, and we can find each integral separately and then add them together. All right, so this is a really useful tool here, where if f of x is defined differently in different places, we can take the integral in those different places and add them together to get the overall integral. Does that make sense? Okay. Just to be clear here, k is just some real number, it's some constant. So if we have a function where f of x now doesn't really depend on x, but it's just a horizontal line. There's our f of x. And we integrate from a to b. How could we find this area right here? Let me clarify here. This f of x is equal to k. Cole?
B minus a times k.
Yes. So b minus a would be the width of that interval, or the width of that rectangle, and k would be the height of that rectangle, so it would just be k times b minus a. And this is just the area of a rectangle. So when we take the integral of a constant, what we're doing is we're taking the area of a rectangle. Keep in mind, if that constant's negative, we're going to get a negative area, right? Okay, next rule. Probably should have saved this one for later because this comes from another one, but we can do it here. So if we take a function, sorry, if we take a function and then we shift it, if we shift it up by a constant k, how is the integral going to be affected? It is going to go up. At least if k is positive, it's going to go up. Yes, Devin got it. So what's happening here is basically we're taking this area, and let me just shade in the area here. I didn't put the A and B on here yet. Let's say we're going from A to B. We're going to take this area right here, and if we shift it up, that area up by k, then what we have underneath it is a rectangle that is k units high and b minus a units wide. So if we shift the function up by some constant, what we're going to do is we take the integral of the function to start with, the integral from a to b of f of x, and then we add on the same thing we got in the last one, the constant times the width of the interval. Does that make sense? Okay. Next rule. This is the one I said we probably should have done first. This is the sum rule. If we take two functions and add them together, and we take the integral of it, what do you think we could do to simplify this?
The integral of each and add them together.
Yeah, take the integral of f of x by itself and add it to the integral of g of x by itself. So this is called the sum rule. If this was a subtraction here, it's the same thing. It's a sum or difference rule, really. So this could be a subtraction sign in here also. And that's kind of the same idea as the last one, except the second function is not a constant. It's a function. How about this? If I take a function and I multiply really every value of the function by some constant, we saw this yesterday actually with one of the examples we did. What's going to happen to the area? You guys remember the example where I took a function, I multiplied it by 2? So every one of the rectangles that we had increased in size by 2. So if we multiply the rectangles by some constant, then the area is going to multiply by that constant. Exactly. So what we can do here essentially is factor out this k. So if we multiply a function by a constant, then we can take the integral of the function without the constant and then multiply that integral by k. And it's kind of like factoring that k out. It's factoring out that constant from each rectangle. Here's two other ones that, well, this is one other one. It's a minimum and maximum rule here. If c is the minimum value of some function on an interval, let me just draw a picture here real quick of what's going on. So there's a, there's b, we have a function. So if c is the minimum value here, then this integral right here of the whole function from a to b is going to be less than the area of this rectangle right here. Or I'm sorry, greater than. Okay, so the green area right here, that's the integral from a to b of the function. This right here is the minimum value of the function on that interval times the width of that interval, which is the red rectangle there. So the area of the rectangle formed by the minimum value and the width of the interval is going to be smaller than the total area. That's kind of a basic idea, right? It seems really simple. This is something that actually leads to the Squeeze Theorem quite a bit when we're trying to prove things about integrals. We're not going to get into that stuff, so this rule here is going to be kind of an obscure one that it's good to know the idea, but you don't necessarily need to know it. This one right here, this one right here is the same thing, but it's saying for the maximum value. if you take the maximum value times width of the interval, that would give us, well, I'll just draw it here. Here's the maximum value. So there's the maximum value times the width of the interval. That's going to be bigger than the integral. Pretty easy, right? And the last one, this is called the Domination Rule. This one's kind of a fun name, right? In this case, we would say that f of x dominates g of x, meaning that f of x is bigger than or equal to g of x for all x values. This is going to be really important when we get back to sequences in series next semester. And it'll work for sequences in series too. So if f of x is always bigger than g of x, then the integral of f of x on some interval is going to be bigger than the integral of g of x. Kind of a simple idea, but really powerful. So that's the last of the rules. I think it's the last one. So I'm going to give you this sheet right here. It has all those rules on it. And if you need to refer to that between now and the test, that's great, but you will not be allowed to use it on the test. Okay?